My name is Boczar. This is Gabe Torres and Jason Suapengco, and we're here to present our project Autoplug, Open Architecture for Automotive Services. Before we go into the description about how our project works, I just want to give you a little background information on the environment that our project's operating in. Last year, 2010, in the United States alone, there were over 20 million car recalls. There was a single General Motors recall. It was a software-related issue that had to recall 1.3 million vehicles, and it cost General Motors $136 million. So obviously, these car recalls can be very expensive to the manufacturer. And with the modern car becoming more and more dependent on software and electronics, naturally more and more of these errors are due to software. Now, the modern luxury car has upwards of 100 million lines of code running on it. For reference, Windows XP that you might have on your home computer has about 40 million lines of code. So these cars are becoming very complex software systems. Now, this software on the car runs on what are called ECUs, or electronic control units. These are small microcontrollers, much like this one here, that operate the different subsystems found in the car. So you'll have an anti-lock brakes ECU, a steering ECU, a cruise control ECU. And these ECUs typically run the control algorithms that operate the electromechanical components of the car. Now, currently, the data being transmitted between these ECUs is somewhat hidden from the manufacturer, meaning they can't always know the software state of their cars out on the road at any given time. This, in turn, makes both the recall and the maintenance process costly and inefficient because car manufacturers aren't able to make well-informed decisions about their cars on the road. What our project, Autoplug, aims to do is to provide car manufacturers with a better way to access this information and remotely diagnose and potentially upgrade the ECUs for their cars out on the road. Now, what often happens today is if you have a software error in your car that needs to be recalled, or more commonly, if the dealer cannot figure out what the source of the error is, what will often happen is that the car manufacturer, through the dealer, will often physically access and replace the ECU with a newer hardware version that has updated software on it. And this is costly to both the user and the manufacturer. With Autoplug in place, the car manufacturer will be able to remotely diagnose the software for its cars on the road and potentially upgrade it with a new firmware if available. Also, with our system Autoplug, car manufacturers will be able to gather long-term data for their cars out on the road in real driving conditions. This could be used in applications such as preemptive maintenance, where car manufacturers could predict both hardware and software errors that could potentially happen, as well as using this data to improve future iterations of cars. So now you know a little bit about why we're doing this project. Now Gabe will give you an overview of how our project works and how we implemented it. Gabe?
Thank you, Ross. So back in September, what we actually set out to do was to create an ECU test bed that we could use to create a software framework that the manufacturers could utilize to take advantage of features such as remote diagnostics, ECU firmware upgrades, and recall management. Autoplug itself consists of 3 layers. We have the simulation or plant layer, the ECU network layer, which is what represents here on the table, and the middleware layer, which acts as a software gateway for the manufacturer to access a vehicle on the road. The simulation or plant layer is an open source simulator running on Linux. It models the physical and the dynamics of and the mechanical dynamics of the vehicle, and it represents our physical car. We couldn't use a real car today because they are mostly closed systems, and we just could not access their electronics. The simulation connects to the ECU network through a data acquisition board. The ECU network itself is a series of microcontrollers that are networked together, and each of which perform an individual function of the car. What you see here is basically the electronic skeleton of a vehicle on the road today, except not in this context. It may not have wheels, it may not have a physical chassis, but in conjunction with the simulator, it represents our model of a car. When Ross turns a wheel, the steering ECU takes input from the steering wheel and passes it over to the simulation layer. The same goes with the pedals. Transmission shifts gears when appropriate. We implement the complex controllers such as cruise control, differential control, and anti-lock brakes. The middleware layer connects to something called the CAN protocol, which is the accepted method of communication between microcontrollers in car today. The CAN bus is the way that each of these ECUs connect to each other and communicate. Using this powerful bus, we can connect the computer to take advantage of the wealth of information that's currently being transferred between these ECUs and perform functions as car visualization for the data being transferred. We could do remote diagnostics and ECU firmware upgrades. It also performs data logging, as Ross said earlier, that allow car manufacturers to perform things such as preemptive maintenance and improve future iterations of the car. Now I would like to proceed with a live demonstration of one of our controllers, which is anti-lock brakes. Now when Ross is driving the car and he engages the brakes, you will see that the car actually turns around 180 degrees. This is actually not the function you want from your anti-lock brakes. We can then run diagnostics on this ECU to see what's actually happening. And we can see that the middleware layer tells us that this ECU is actually working incorrectly. We check for things as settling time, whether the car is actually still going in the direction it was going in, and we can tell that the ECU is actually working incorrectly. Now, what generally happens is if there's a software error in a controller in your car, you generally take it to your dealer. The dealer will have to physically access and remove it to replace it with a brand new one. This is costly for car manufacturers if your car is under warranty, and costly for the user if it's out of warranty. We don't see a need to do this if it's just only a software error, as we can just upgrade it using our system. The way that ABS is supposed to function is by normalizing the speed of the wheels to the speed of the vehicle, so that when icy or slippery conditions, the driver does not lose control of their car when they enable their brakes. Now we should see Ross enable the brakes, and the right operation should be found. We can see the brakes pulse to normalize the speed of the wheels, as we see in the graphs. Now Jason will take you through another scenario in which our system will be useful.
In addition to anti-lock brakes, this Autoplug could be used on any of the 70 to 100 ECUs in the modern vehicle. For example, in addition to anti-lock brakes, we have the system implemented for cruise control. When Ross drives the vehicle, we can see that when he initiates cruise control, instead of maintaining the same speed, the system will be unstable and the speed and the acceleration will vary. Using Autoplug, we could run diagnostics on this cruise control, and what this is doing is that it's taking the speed at which cruise control was set, finding the average speed when diagnostics was initiated, and finding the error and variance in that error. As we can see from the diagnostics, the variance is extremely high, indicating a faulty cruise control, and through Autoplug, we can actually upgrade the firmware of the car, which is the same as we did to anti-lock brakes. And Gabe will explain a little bit about how the firmware is being upgraded over the CAD network.
So what's actually happening now is that the middleware layer is sending a signal to the microcontroller to jump to a bootloader that was implemented in the controller itself, that waits for messages to replace the actual firmware that is existing on the car today, on the controller right now. This will enable us to generally replace the code that is in the controller and restore proper function.
Now that cruise control has been completed upgrading, when Ross initiates cruise control, we can see in the simulation that the acceleration no longer accelerates and decelerates, and the system's no longer stable, and it's running very smoothly. And we could run diagnostics again to show that indeed the cruise control ECU is working correctly. In the future, if Autoplug were to be implemented by car manufacturers, the users could actually have a smartphone where they can actually view the information being sent to the manufacturer from their vehicle, and the manufacturers for passive and non-critical components can send the user an upgrade notification similar to how Microsoft deploys updates to Windows computers, and the user can verify this upgrade as such. Now Ross will talk a little bit about the future of Autoplug.
Okay, so when we started this project, the scope of our project was to be able to remotely diagnose and upgrade these ECUs, which is primarily a safety concern for cars today. If this project were to be taken to the next level, obviously security and privacy would be two main steps that car manufacturers would have to worry about, especially considering remote upgrades of the ECUs in a car from the remote location. So if Autoplug were to be taken to the next level, those would be the next steps that would need to be addressed. I guess if you've been watching TV over the last 6 months or so, you might have seen commercials for major car companies such as Ford, GM, Volkswagen have all come out in the very recent past with smartphone applications, much like the one Jason showed you earlier, which are starting to share some of this data to both the user and the manufacturer. For instance, I think there's a Ford one that shows your oil level, shows which doors are locked and unlocked, shows which doors are open, things like that. So Autoplug is definitely being implemented in an area of automobile technology which is very active right now. Also, we've been in contact with industry representatives from both Ford and Toyota, and they both, as you can see, have a lot of positive feedback about this project. So Autoplug is definitely operating in an area where automotive technology is trending toward, meaning this sharing of information between a remote location and the car manufacturer. So, in summary, this is our project Autoplug, and it provides car manufacturers with a better way to access the information on the car and to potentially remotely diagnose and upgrade these ECUs. Thank you for listening to our presentation, and we'd be happy to answer any questions you might have.